Unit 4 is periodic trends of the elements, and the first trend I want to discuss is effective nuclear charge. Now, the nuclear charge is based on the number of protons, and it's predictable that as you go from right to left in a period, the nuclear charge or the effective nuclear charge increases. What is strange, though, is that as you go down a group, as you go from top to bottom on the periodic table, even though you're increasing the number of protons, the effective nuclear charge is actually decreasing. And I'll explain that in this video. Before we take a look at those specific trends that I just mentioned, let us take some definitions down. And the first one is nuclear charge. Nuclear charge is going to be a whole number, and the abbreviation for nuclear charge is Z, and we know that that equals the number of protons. Each proton we'll consider as a +1 charge. Okay, so 1, 2, 3, 4, etc., depending on the number of protons. But there's another type of charge that we're more interested in. It's called the effective nuclear charge, the charge that the electrons actually feel. Effective nuclear charge. The abbreviation for that is Z with EFF as a subscript. And that is the actual magnitude of positive charge felt by electrons. And later on, we're going to specify, normally what people are interested in is the charge felt by the valence electrons. Those are the electrons that are on the outer edge of the atom involved in bonding. But why don't I give you a picture of what this looks like? You have a nucleus. Let's say your nucleus has two protons. Two protons. Hence, your nuclear charge is going to be 2, but you normally do put the sign there, +2. And then you have electrons, and your electrons are in orbits, or we should call these energy levels. And let's say we have 2 electrons, so this is going to be the helium atom. 2 protons, 2 electrons, and we're going to abbreviate the electrons with an E superscript negative charge. E superscript negative charge. Those electrons are feeling an attraction to the protons, so it takes energy. It takes energy to kick them out of the atom, and for the first electron, it takes 3.94 times 10 to the minus 18 joules to make that electron leave the atom. Okay, but what about that second electron? You, that second electron is actually feeling a different charge now that the first electron has left. So this is still +2. The protons have not changed, and we have another electron, the second electron here. To kick that one out, it takes more energy. So even though the nuclear charge stays the same, the electrons feel something different depending on how many other electrons are with it. And this number is higher, much higher actually, more than double, 8.72 times 10 to the minus 18 joules. That is because in this situation, the electrons are shielding each other from the full force, the full attraction of the protons. All right, I do want to jot this down. So why is this so complex? Because electrons uh, also feel other electrons. And we have this phenomenon called shielding. That's our third term. We have nuclear charge, effective nuclear charge, and then, why is it crooked? Shielding. Let me raise this up. Shielding. How electrons modulate the actual charge felt, okay, we'll put these in quotes, by other electrons. Okay, let's take another atom. Let's take, oh, I need my periodic table. Let's take, oh, magnesium. Yeah, let's take magnesium, 12 electrons. And let's write the electron configuration. Magnesium has 12 electrons when it's neutral. 1s2, 2s2, 2p6, 3s2. 3s2. Because we have to be concerned about shielding, we have to know which electrons are the most effective at shielding. And actually, it's the ones closest to the nucleus. And it's actually all of these. All the electrons that are not part of the valence shell. You know this 3, that is considered the valence shell. So there are 2 valence electrons. And that leaves behind, or that leaves for us 10 what's called core electrons. Core or inner electrons. And these are the most effective at shielding the charge. So core or inner electrons are the most effective. Okay, now Z is easy. Z we could list because all we have to do is know the number of protons, and we get that from the periodic table. The effective nuclear charge is going to be less than Z, because if Z is, for instance here, +2, but these electrons are modulating how they each feel this charge, then they feel less of this charge. They feel less of this charge. Let me give you a table. Let's have Z here and Z effective, or effective nuclear charge. And we are going to go across the period number 2. Lithium, beryllium, give yourself some space, boron, carbon, nitrogen, oxygen, fluorine. The Z is easy. It's a number of protons. We start with 3 protons for lithium. 4, 5, 6, 7, 8, 9. Okay. The effective nuclear charge, the charge actually felt by the electrons when the atom is that full with the number of protons and electrons, is going to be less. And this is all done experimentally, 1.28. You are not expected to know how to calculate this. Give me 1 second. Oh, 9.1. 2.42. I'm not going to show you all of them. 3.14. Let's stop there. So while, as we go across the periodic table, we add 1 to the charge, or the nuclear charge, we don't add a full 1. We add less than 1. 0.63. From 4 to 5, we add 0.51. Over here, plus 0.72, the difference. So again, you're not expected to know, or you're not expected to calculate this Z effective. And it varies. It's kind of hard to predict how much you should add. Okay, but always you're adding less than 1 every time you add 1 proton. So this is the charge. Okay, you could think of it as a plus 1.28, plus 1.91. That's felt by the electrons. Now, there is an equation. It's called ZF equals the nuclear charge minus some shield constant factor. So yeah, maybe you might be given this sigma, and you just have to know the atomic number, the number of protons. And this is called the shield constant. And it's by experiment. It's gotten experimentally. Okay, let me actually revise this definition here. This definition is true, but in practice, what you should be thinking about is how the valence electrons feel this charge. So we have effective nuclear charge, actual magnitude of positive charge felt by, let's put valence electrons. Technically, it's by all the electrons, but we're most interested in the valence electrons because those are the electrons that are most likely going to be ejected when we hit it with a pulse of energy. Those are the electrons that are most likely to be transferred in a ionic bond. And those are the electrons that are involved in covalent bonds. All of that is actually in a different unit in the future. Let me now repeat the trends, okay? Because we have already a trend here. As you go across the period, your effective nuclear charge gets higher. I do want to formally jot that down. And I like to show a little diagram of a periodic table. So for instance, if the periodic table has a general shape like this, okay, and the first trend that we saw in this video is that as you go across the period, if you go from left to right within a period, that's important. A period is a row. Z effective, what does happen? It increases. Increases. Let me just make sure I'm not missing anything super important. Yeah. But what about going down? We might see something surprising. Or this result might be surprising to some of you. By the way, the effective nuclear charge increases because the charge increases, or the Z increases. But the weird thing about going down a column, or let me just say this a little bit differently. Well, no, I'll do it that way. Going down column, or that's a group. So as you go from top to bottom in a group, okay, a group is now the column, the ZF does something strange. It actually decreases. Actually decreases. And I'm going to put not a star, but I'll put exclamation points because that's surprising. Because why? Doesn't the number of protons increase as you go down? So even though Z increases, okay, that's because as you go down a group, you're increasing the n value. So what's the explanation here? It's because you're increasing the n. Remember n from quantum numbers or the Bohr model, n equals 1, 2, 3, 4? Well, you're getting bigger. N, because increasing n, or this is called the shell number, and you are getting bigger. So n equals 1, n equals 2, n equals 3. Sorry about that. And then you have the nucleus. So as you get farther from the nucleus, wouldn't it make sense that those valence electrons, the electrons in the valence shell or the outer shell, don't really experience the full charge of this nucleus. Plus, you have a lot of core electrons in between them. Okay, this is just a very simplistic view or cartoon, but yeah, as you get farther away, you're feeling less of that charge, and the Z effective again decreases. Z effective decrease, which is again very strange because we're adding more protons, but as you go down a group, your n value increases as well. See, for the period, the n value stays identical, stays the same. Okay. You could even say here that the atom gets bigger. Atom gets larger, and valence electrons get further away, much further away. Hence, the effective nuclear charge goes down. Now, the way that I like to draw the diagram is my arrow is going to indicate how the trend increases. For effective nuclear charge, it increases how? It increases as you go to the right, and it increases as you go up. So this is increasing. Z effect, or effective nuclear charge, which is kind of strange again because look what has the lowest Z EFF. It's the one in the bottom left, francium. Even though it has a lot of protons, it has the lowest effective nuclear charge. Okay, that's because the valence electrons are so far away from the nucleus. That's all I want to say about effective nuclear charge and shielding. Just keep in mind of this little hiccup or this. At first it's counterintuitive, but if you think about the atom getting much bigger as you go down the group, then it does make sense that those valence electrons don't feel a very large charge. Plus, you have all those inner electrons as you get bigger and bigger in size. And the full summary really is just this. Okay, let's double check again. I really want to make sure my arrow is drawn correctly because the effective nuclear charge decreases as you go down, so it increases as you go up. So this arrow goes to the northeast. Ah, what does that mean? The biggest, uh, the biggest effective nuclear charge is we're gonna go with helium. Oh, definitely helium, because its electrons are in the n equals 1, and there are 2 protons attracting it. So it even has a stronger effective nuclear charge than hydrogen, because hydrogen only has 1 proton, but they're in the same period. So within the same period, you go by the number of protons. All right, the next video, we're going to look at the other trends on the periodic table. But this is our first effective nuclear charge.